So, hello Year 12 and welcome to the first of I don't know how many videos trying to remind you what we've done this year on the inorganic side of the AS course. And starting with the biggest topic and the one that we did first of all, probably to scare you, back in September and October, which was topic 5, formulae, equations and amounts of substance. And I'll change to a pointer. As you can see here, part 1 of probably 2. This is the first half of the spec. Some of these things you should recognise from GCSE, knowing what a mole is, knowing what the molar mass of a substance is, calculating amounts of substances for mass, volumes of gas, volumes of solution and concentrations. So they're the 3 mole equations that you know from GCSE, reacting masses, and volumes of gases using amounts of substance. All of those should have been covered at GCSE. You may also have looked at the Avogadro constant at GCSE. There are a couple of questions that specifically asked you how many molecules there are in a mole, but you may have forgotten that. And also Ionic Equations, something I know that lots of teachers don't really go into lots of detail at GCSE because it's very high level. Unfortunately, you do need to know those for AS level. So let's go back to the beginning. And one of the very first things that we did was we reminded you how we could start to put various things together to work out the formulae of ionic compounds. And a reminder, main block elements, it's fairly straightforward to work out what their charge is going to be. Group 1, for example, has 1 electron in the outer shell. It will lose that electron to form a 1+ ion. Ditto, group 2 always form 2+ ions. They have 2 electrons in their outer shell. On the other side, over here, the halogens, group 7, they've got 1 gap in their outer shell. They take 1 electron to form 1-, and so on. Group 4, of course, being quite interesting, having half full shells. It's quite difficult for them to gain or lose electrons, and therefore they'll do something else, covalent bonding. So what about the transition metals? Well, the key rule here is presume 2 unless told otherwise. So things like zinc, 2+, always 2+, but it can be anything from 1 to 8. And some things have a high number of different oxidation states. So manganese can be anything from 2+ to 7+. You'll often be told, for example, iron 2 chloride versus iron 3 chloride. And of course that gives you the charge, or more correctly, the oxidation state of that particular element. There is one that you need to know, and that is silver, which forms the 1+ ion. And of course you should know from studies in the other half of the course that that's because silver has 3d10 for S1 in terms of the electronic arrangement. It fills its D subshell at the expense of the S subshell, and therefore it's got 1 outer electron that will use. These ions you do need to know. We've said this since GCSE. Many students still haven't bothered to learn them even at this stage, and I know even a few weeks ago some of my students still did not know the formula and charge of things like sulfate and phosphate, but you do need to know these. Make sure you know the formula and the charge of these polyatomic anions. In particular, lots of my students still not knowing the difference between ammonia, NH3, and ammonium, NH4+. Okay, so make sure you get that right. Most of the rest of them are fairly straightforward. So you should be able to answer questions like this, and by all means pause the video and have a go at working out the formula of some of these things. Do be careful of the difference between, for example, sulfate and sulfide, nitrate and nitride. So sulfide here, silver sulfide. We've got silver, Ag+, as we saw on the previous slide. We've got sulfide, that's sulfur, S2-. And when we work out that these two have to form a neutral compound, it's clearly Ag2S. A similar example would be magnesium nitride. So up here nitride, not nitrate. So we've got, if I can find my pointer, wherever it's gone, magnesium. No, totally wrong place. Yeah, there we go. Magnesium 2+, and nitride. So this is the nitrogen anion, N3-, so Mg3N2, in order to get a neutral molecule there. You might have noticed by now that I'm struggling with new technology, so feel free to laugh at me for that one. Balancing equations, again, feel free to pause this video and have a think about balancing these equations. But here are the answers, so you can check how you did. And a skill that we presume you can do at GCSE, and we'll continue on to A-level. One of the first things you did that was new was, if you remember, you did a quick experiment, solubility rules, and you looked at copper 2 chloride, iron 2 sulfate, etc. And you worked out what they looked like, whether they were soluble, and you looked at the formula. We reminded ourselves about where there are hydrated complexes, and so you've got iron 2 sulfate, heptahydrate. There's 7 water molecules there built into the molecular structure, or sorry, the structure of those crystals, and they are part of the structure. There's a very defined number in some cases, so 9 in iron 3 nitrate, 2 in copper 2 chloride, and they of course have to be taken into account when you're working out the relative molecular mass of hydrated crystals. So you needed to know your solubility rules. I hope that's been hammered into you by now. And so have a think, pause the video, think about what your main solubility rules are. So hopefully you came up with something like the fact that all ammonium, potassium and sodium salts are soluble. They're always soluble. Ditto, all nitrates are soluble. So if you want a salt that is soluble, so lead nitrate or silver nitrate, for example. Halides, fairly straightforward. They are mostly soluble except for lead, a very common exception, and silver. And you should know from your topic, your group 7 topic, that we use silver nitrate to test for the different halides, and we get different precipitates with the 3 different halides. So silver chloride is white, silver bromide is cream, and silver iodide is yellow. In terms of sulfates, most of them are soluble. The exceptions are lead again, and barium. And this comes in quite a lot later on. So what you've just done in group 2, you've looked at the solubility of the sulfates, and you found that they get less soluble as you go down the group, hence magnesium and calcium soluble, but barium sulfate is not. And again, that is a test that you know from GCSE. Most carbonates and hydroxides are insoluble. That's the general rule. If you really want, you can tie this again in with the stuff that you did in group 2 just now, where you find out that the group 2 hydroxides get more soluble as you go down the group, and therefore barium and to some extent calcium hydroxide are soluble. On the back of that was something that a lot of you hated, and I'm not sure that you ever really got to grips with, which was, what is an ionic equation? And just to really point out, an ionic equation is just there to show you the actual reaction that is going on. It removes all of those components that are sitting by and doing nothing. So here's an example from GCSE. You take silver chloride and you react it with silver nitrate solution, and you see what you get at the end. And you get a precipitate of silver chloride, and the sodium and the nitrate ions are left in solution. Well, we can see that the sodium ions are unchanged at the end of the reaction. They don't do anything. And ditto, the nitrate ions are not part of that reaction. They're sitting there at the beginning doing nothing, they're sitting there at the end doing nothing. So the real reaction is between the chloride ions and the silver ions to form a silver chloride precipitate. And that's what we want to get at, the actual equation going on. Here's another example. So putting iron into copper sulfate solution. You did this practical when you were trying to work out the formula of the iron sulfate that was produced, I think, and you end up with a different set of products. You end up with that brown copper colour being formed as copper is displaced by the iron. You end up with iron sulfate in solution. But again, looking at this, we can see that the sulfate ions are not part of the reaction. The iron atoms have become iron ions, the copper ions have become copper atoms. So what's going on essentially, and that's what the Ionic equation is trying to tell us, is that a copper ion bumps into an iron atom, they exchange a couple of electrons and they form an iron ion and a copper atom. So how do we get to that? Well, first thing, and one of the big mistakes, you don't do anything with pure metals. Pure metals are pure metals. You put a metal into water, it's still a metal. Sometimes it reacts with the water, but it's just a metal. It doesn't dissolve, it's not charged, you just leave metals as is. Ditto, covalent molecules, don't touch them. Bromine is just bromine. Iodine is just iodine. Methane is just methane. Hydrogen is just hydrogen. They don't break up, they don't ionize, you don't have charges, you just leave them. If you've got insoluble ionic compounds, so in the previous examples, a couple of examples ago, we made silver chloride. You don't touch them. Why? Because the silver and the chloride ions are actually bound together. They can't separate. We call it silver chloride, it is silver chloride. We call it lead iodide, it is lead iodide. So that's exactly what it says on the tin. But the things that are different, these are soluble salts. Anything that dissolves in water actually separates. So we call it sodium chloride, but it's not sodium chloride because it's completely separate. In fact, it's two different chemicals. It's sodium plus ions and chloride minus ions floating around. They're not doing anything together, they are completely separate. So as soon as they are dissolved, the positive and negative ions behave completely independently, like two different chemicals. And this is why we separate those things. So in order to get an ionic equation, you need your word equation, which you will hopefully be able to turn into your balanced chemical equation. And then you need to look and say, well, which of these species actually split up? Which of them are genuinely not what it says? And in this case, the metal iron is just a lump of iron metal. That is what it says on the tin. The copper is just a lump of copper. That's what it says on the tin. But the copper sulfate and the iron sulfate are not copper sulfate and iron sulfate once they're dissolved. They are copper ions and sulfate ions, iron ions and sulfate ions. And when you do this, you notice that the sulfate ions aren't doing anything. They're just watching the reaction. And so they can be removed to give you the final ionic equation, which we looked at a couple of minutes ago. So the real reaction occurs when an iron atom gives 2 electrons to a copper atom. Iron is oxidized, copper is reduced. Here's another example and the balanced chemical equation. So have a think, what do we split up? Well, we don't split up the chlorine, that's covalent. We don't split up the bromine, that is a covalent molecule. Even though it's dissolved in water, it is a bromine molecule, Br2. That describes exactly what the thing looks like. But the potassium bromide and the potassium chloride are split up. They are different things, so they can be can be split up. And when we look at this, we can see the potassium ions do nothing. They are the spectator ions, and we can cancel those. So our final ionic equation is that a chlorine molecule bumps into a couple of bromide ions, forms chloride ions and bromine So that was the first couple of weeks. Then we went on to look at moles. And just to remind you, all a mole is a group of particles. People often define a mole as Avogadro's number, but that's not really what it is. Yeah, it's that number of particles, but a mole is just a certain number of particles. So we've got a box here, we've got a mole of oxygens. We could remove all of those, and we could instead, into each gap, we could put a water molecule, and we'd have a mole of water molecules. The crucial thing is that a mole always has the same number of particles. That number of particles, which you do need to know, it's going to be helpful if you know that number, so you're not always having to look it up, 6.02 times 10 to the 23, that's Avogadro's constant. And the interesting thing is that Avogadro never actually knew that number. It was only determined 54 years after his death in 1910. You don't need to know the number of particles in a mole to be able to use it. And that's why when students define the mole as 6.02 times 10 to the 23, they're kind of missing the point. If we look at these two boxes, 1 mole of helium versus 1 mole of xenon, they contain the same number of particles, but because xenon particles are 33 times heavier than helium particles, the box on the right would be much heavier. Just an aside here, hopefully you remember that oxygen always goes round in pairs, chlorine always goes round in pairs, and thus if we talk about a mole of oxygen gas, each of those slots is taken up by an O2 molecule, so the whole box, the whole mole would be 32 mass units, 1 mole of oxygen is 32 grams, and the same idea with chlorine. And again, remember, 1 mole is a specific number of particles, which isn't necessarily atoms. It can be ions, it can be molecules, or it can be a particle of an ionic solid. Relative formula mass of carbon dioxide. Carbon is 12, each oxygen is 16, so that gives you 44 grams per mole. The units mean that 1 mole weighs 44 grams. That's what that means, 44 grams per mole. 1 mole weighs that amount. And at GCSE, you would have been used to these triangles. I really hope by now that you don't need them. In fact, you can just look at the units, grams per mole, to realise that the formula mass must be mass over moles, and you can rearrange from that if you need to. 2 moles of cesium iodide, of course, 520 grams, if you're wondering what that little quiz in the middle was. We need to be specific when we're using the mole, because if we are asked how many moles are there in 64 grams of oxygen, it depends on what we're talking about. If we're talking about oxygen gas, then there are 2 moles because each O2 molecule is 32 grams per mole. But if we're talking about atoms, so we're talking about a compound that contains 64 grams of oxygen, we're not really interested in O2, we're interested in oxygen atoms, and in that case there'd be 4 moles. If we're being really weird, we might be talking about ozone, in which case there would be 1.33 moles of ozone. So you do need to know what you're talking about. Think carefully. Are we asking how many moles of oxygen atoms there are, or oxygen molecules? Now, something that students really struggled with, and I don't understand why, because actually it's a really simple concept, is just working out the number of atoms. And given that students can easily work out the number of moles of something, and they know the number of particles in that mole, I always find it very strange that they can't link the two ideas together. But let's say we were asked how many atoms are there in hydrogen atoms in 90 grams of water. Well, if we know that 1 mole of water weighs 18 grams, then we can quickly get to the fact there's 5 moles of water, and none of you would have a problem with that. You'd all be able to tell me that. But here's the key thing. Each of those moles holds 6.02 times 10 to the 23 particles. So we can quickly get to the number of water molecules in the box. Okay, so there's that number of water molecules. We want to know how many hydrogen atoms there are. So all we need to do is say, well, if we've got 3.01 times 10 to the 24 of those, there's 2 hydrogen atoms in each molecule. So we just multiply that number by 2 to get that we've got 6.02 times 10 to the 24 hydrogen atoms. As another example, let's say we're asked how many hydrogen atoms there are in 100 grams of methane. Have a think, pause the video, restart when you have an answer. Okay, well, we know that 1 mole of methane, 1 box of methane is 16 grams. So we've got 6 1/4 moles of methane. And again, I suspect that the vast majority of you were absolutely fine with that idea there. Again, Avogadro's number. Each mole contains this number of particles, 6.02 times 10 to the 23. So we know the number of methane molecules. But this is the bit where people get stuck, trying to translate that into the number of hydrogen atoms. Well, again, all we need to do is think, well, here's methane, 1, 2, 3, 4 hydrogen atoms. So if we know there's that number of molecules, we times it by 4, and we get an answer of 1.51 times 10 to the 25 hydrogen atoms. It's quite straightforward. Students struggle. Make sure you can do those questions. Another thing is the idea of the empirical formula. And I have my trusty calculator here, so I will be doing these live. So find the empirical formula of each of the following substances. Well, we've got 20.2% aluminium, so that's 20.2 grams. Divide by the relative atomic mass of aluminium, which is 27, and we get an answer of 20.2 divided by 27 is 0.748. I didn't mean to do that. 0.748 moles of aluminium in 100 grams. For chlorine, we'd have 79.8 divided by 35.5. This is atoms, right? This is why we're not doubling it. It's not the number of chlorine molecules, it's the number of chlorine atoms. And if we do that, 79.8 divided by 35.5 is 2.248. We can look at these numbers, maybe divide both of them by the smaller number, divide by 0.748, and not surprisingly, if we divide that by 0.748, divide that by 0.748, we get a ratio of 1 to 3. That's pretty much exact. Oh, it went right. For some reason, 1 to 3, telling us that the empirical formula is AlCl3. Now that's the empirical formula, that's the ratio of atoms. It might not necessarily be the actual formula of the molecule. And as an example, look at ethane up here. The molecular formula, C2H6, but in terms of a ratio, the empirical formula, CH3. And again, the same might be true of this aluminium trichloride. We know it can pair up. It might be Al2Cl6. From GCSE, you should be happy to do any of these conversions, mass to moles, gas to mole, or a solution, concentration and volume to mole. And coming out the other way, mole to mass, mole to solution, mole to gas. Of course, the bit in the middle, this is the key bit where you use the balanced chemical equation to tell you what's the ratio of the number of moles, and you should be able to do those even without learning these three equations at the top. You should just be familiar enough now that it makes sense which way round they are. Here's an example, pause the video if you want. What volume of carbon dioxide is made when 50 grams of calcium carbonate is neutralised? So, here's the equation. I'm hoping you know that and you didn't need to look it up. Calcium carbonate plus hydrochloric acid. Oh, I didn't say with hydrochloric acid, sorry. You might have struggled there. With hydrochloric acid forms calcium chloride and water and carbon dioxide. And and so we can go from the mass, 50 grams of calcium carbonate, to moles. Moles is mass over formula mass to give us half a mole of calcium carbonate. We can see from the balanced chemical equation that it's a 1-to-1 ratio. So we have 0.5 moles of carbon dioxide. Hopefully you remember from GCSE that 1 mole occupies 24 decimeters cubed at room temperature and pressure, and therefore volume is 0.5 times by 24 decimeters cubed, which gives us 12 decimeters cubed of carbon dioxide. We looked at core practical 1, which is where you had to measure the molar volume of gas and you had to kind of confirm for yourself that 24 decimeters cubed. Reminding you again, 32 grams of oxygen gas, 32 grams, 32 divided by O2, which is 32, gives you 1 mole. So that is 24 decimeters cubed. Nitrogen gas, ditto. 1 decimeter cubed, 24 decimeters cubed, 1 mole. 71 grams chlorine gas is the same, but helium down here, helium is only half a mole, so that would be 12 decimeters cubed. So that's the odd one out. In your potential procedure, you reacted something like magnesium or calcium carbonate with hydrochloric acid. You used a gas syringe to collect the gas, and you had to work out the molar volume from the number of moles of gas that were produced. In this case, your acid was limiting, and that was to overcome the problem of maybe the magnesium or the calcium carbonate not being pure. So you did need to be able to identify the major sources of error that were being caused in this practical. And there were a few of those. There was the fact that it was difficult to get the bung on instantly, so some of the gas would escape before you could put the bung on. There was the fact that when you pushed the bung on, it did cause a 0 error in the measuring cylinder. Obviously, you would have leaky equipment, the lack of pure reagents. Any of those could have caused sources of error. If you were producing carbon dioxide, another source of error, especially if you're collecting it over water, is the fact that carbon dioxide dissolves in water, and that would cause a big problem with the amount of CO2 you were collecting. One thing it specifically says in your spec is you've got to be able to quickly go from gas volume to gas volume. So let's just recap that. What volume of carbon dioxide is made when 12 decimeters cubed of pentane are burnt? Well, if we got 12 decimeters cubed of pentane, we can work out that that is half a mole of pentane. From the ratio in the equation, 1:5, we can say that would make 2.5 moles of carbon dioxide, which would be 2.5 times 24 decimeters cubed. In other words, 60 decimeters cubed of carbon dioxide gas. But there is a shortcut. Essentially, you can realise that you're dividing by 24 just to multiply by 24. And therefore, the simplest thing to do is just look at the ratio in the equation. So here, what volume of carbon dioxide is made from 40 decimeters cubed of oxygen? Well, so we got 40 decimeters cubed of oxygen. The ratio of the coefficients is 8:5. So the volumes will be in the ratio 8:5. So 40 divided by 8 times by 5 gives us 25 decimeters cubed of CO2. And you've got to be able to do that fairly rapidly. So if it's a gas to gas, same conditions of temperature and pressure, you can just use the ratio of the equations. Which brings us on to the ideal gas equation. So PV equals nRT. The pressure of the gas times the volume of the gas is the number of moles of the gas, assuming it's an ideal gas, times R, the ideal gas constant, times by T, the temperature. But the key thing here, it's really straightforward as long as you remember the units of these things. Remember that the volume must be in meters cubed, and many people, despite me saying that so many times in the year, were still insisting on putting the volume in decimeters cubed. The pressure must be in pascals, less common, but several people forgetting to convert kilopascals to pascals, And of course the temperature must be in Kelvin. Several people forgetting to make that conversion. So just to remind you, 1 kilopascal is 1,000 pascals. Atmospheric pressure is 100 kilopascals, so that's 100,000. To convert Celsius into Kelvin, you add 273 Kelvin, which in this case would be 298 Kelvin, a number that should look quite familiar with you. 1 meter cubed is 1,000 decimeters cubed, which is 1 million centimeters cubed. And again, people really not converting centimeters cubed properly all the way back into meters cubed. So do watch out for that. If you get that right, actually ideal gas questions are fairly straightforward. So here you go. A helium party balloon has a volume of 18 decimeters cubed. At 25 C, the internal pressure is 108 kilopascals. Calculate the mass of helium in the balloon. Well, we start off with N. So PV equals nRT. So N equals PV over RT. The pressure is 108 kilopascals, times that by 1,000, 108,000. The volume, okay, so the volume is 18 decimeters cubed, so we need to divide that by 1,000 to put it into meters cubed. R, the ideal gas constant, 8.314, and the temperature, 25 degrees C, so 25 plus 273. Now, I know some of you will be tempted to just stick all of that into your calculators. If you do that, you're bound to make an error. Maybe just work it out, okay? Leave some intermediate steps. But if you do that, you should find out, putting all that together, that the number of molecules is 0.785 moles. Sorry, the number of moles, 0.785. And therefore, you can multiply that by the mass of the mole, which is 4 grams per mole, to get 3.14 grams, okay? So, sorry in advance that I didn't give you that last step, but yeah, you get the number of moles and then you can multiply that by the mass. Just go through and tick off, what do I have? Am I given the pressure? Yes. Am I given the volume? Yes. Am I given N? No. Am I given R? Yes. Am I given the temperature? So I must be finding N. Even if you weren't quite sure what to do, you find N. And then, of course, you realise that the number of moles is the mass over, it's all gone wrong again, over the molar mass. So number of moles is mass over mol. Here's another example. A sample of gas has a volume of 445 centimeters cubed and a mass of 1.5 grams at a pressure of 95 kilopascals and a temperature of 28 degrees C. Calculate its molar mass. Again, so what are we given? We're given V, we're given the pressure, we're given the temperature, so we're going to have to work out N. So N equals PV over RT. So the pressure, again, make sure we put it into pascals, 95,000. The volume is given in centimeters cubed, 445, divided by 1,000,000 this time, because we need to put it into meters cubed, over R, 8.314, times by the temperature, again, 28 plus 273, and that will give us the number of moles of gas. From that, we know the mass of it, so from the equation, number of moles is mass over mR. We now know the number of moles and we know the mass, so we can work out the mR. It's a bit messy down there, but you can see that it eventually works out at 88.8 grams per mole. Final thing, don't freak out if you're given a question like this, where you're given a density. Essentially, you can do the same thing. You just start by saying that one decimeter cubed equals 1.65 grams. And then if you've got that, pressure, yes. Volume, yeah, we've chosen 1 decimeter cubed. N, no, we're trying to find that. R, we can look for, we've got, and the temperature, we've got that. So we can find out the number of moles. Again, we've got from this that N is the moles over molar mass. And we can work out N from the first equation. The mass for a decimeter cubed is 1.65 grams. And then we can work out the MR, and it works out at 44.7 grams per mole. Okay, well that looks like the first part. Please do email me if there's anything that you need. Just to remind you, my email address is I'm giving up right now. a.nixon, Nickson, at ulstergs.com. There'll hopefully be another one of these at the end of the week going through the second part of topic 5. I'm going to put some questions online for you. There'll be multiple choice and a quiz on show my homework. So feel free to just enter the right letters and it should be self-marking and give you some feedback. The questions will relate to what I've just gone through in the PowerPoint already. Okay, cheers, thank you.